Okay, this is the thesis defense of Ben Corbin on the Aeroastro chair. And see, I've known Ben actually since you were an undergraduate. Ben won an astronaut scholarship, and I'm on the Astronaut Scholarship Foundation Committee. So I first met him then. He came here as a master's student. I was his advisor. When Ben said that he's interested on the one hand in aerospace engineering, but also planetary science, and it turned out there was an opportunity over at BU. There was a sounding rocket experiment, and they needed somebody, and this was to look at the atmosphere of Venus, so it was planetary science, but they needed an engineer to make sure that it would all work, and that really fit Ben's desires. It takes a little longer sometimes to get a sounding rocket launched than you would all often like, but Ben did a nice master's thesis with that, and continued his interest in planetary science and aerospace engineering with his current thesis topic, which we're going to hear about now. So Ben, take it away.
Thank you, Jeff. Today I'm going to be talking about the value proposition of distributed satellite systems, otherwise known as how can we accomplish new scientifically interesting missions using the emergent capabilities of distributed satellites. How can we go about using them in such a way that we can do things that we cannot do with single satellite systems? So the focus of this talk is thinking about whether or not we can do things that we've never done before because we can use distributed satellites in ways that we can't do with single satellites. So let me go over a little bit of an introduction of what I mean by some of that, and then we'll get into the real details of this. So single satellite systems are often cheaper. They're definitely more in use nowadays. They are prone to single point failures though, so if you lose part of it, you might lose your entire satellite system. Whereas with distributed satellites, there's a lot of redundant elements, so the cost can go up. But as a result, there's a number of system lifecycle properties, also known as ILIDs, such as changeability, reconfigurability, upgradability, that can give benefits to the system. However, those benefits don't necessarily add directly to the value proposition of those missions. Some of these indirect benefits are very difficult to quantify as a result of this. So really, one of the things I wanted to ask was how can we directly contribute to the life cycle value of these science missions with distributed satellites? So I looked at what was called emergent properties, where if you have a quality that arises as a result of multiple elements working together. Think about it, if you can't model the entire ocean if you only know how to model one water molecule. It's the emergent properties of the ocean that result from many different water molecules interacting together. What I define it as emergent capability is it's an ability that arises as a result of those multiple elements working together, where any single one of those elements does not have that ability. So one of the things I was looking at was how do these emergent capabilities affect the system lifecycle of distributed satellite systems, or DSS, and how can they be used to accomplish new, broad, fundamental science goals? So that brings us to our two primary research questions. Research question number one, what emergent capabilities can be demonstrated and achieved with distributed satellite systems that you cannot achieve with a single satellite? And how do we go about ranking those designs alternatives that we can come up with? How do we characterize those systems, and how do we choose which design would be best for the mission that we're trying to accomplish? So these are the two primary research questions, and we'll be coming back to those throughout the presentation. So the approach I took was a four-phase approach, starting with knowledge capture and synthesis with literature reviews. Those literature review parts fed into how we could define these emergent capabilities. They fed into the development of the method that we were going to use, and all three of those fed into the space science mission case studies that we're using as empirical evidence to demonstrate that we've solved these questions. So there were also feedback from those case studies that led into another iteration on how we can define those emergent capabilities. Also feedback from the definitions into the method, so we could reiterate on those and come up with a more generalizable approach for ranking systems in a pre-phase A concept study. And then from the case studies themselves, we have scientifically unique missions and an overall how-to framework for scientists and engineers to plan these missions. So we'll start with the knowledge capture and synthesis right here. There's a lot of research motivations that went into this. It's kind of hard to condense it all into one area. One of the things that led to this research was the cancellation of the F6 program. Fractionated satellites, otherwise known as satellites that kind of operate on a local area network. You can plug and play different elements. That program failed partially for reasons they weren't exploring the emergent capabilities. They were exploring some of the indirect benefits, but they weren't necessarily adding to the value of that mission directly. One of the problems they had was, how do we evaluate these missions in the pre-phase A studies? So in the systems life cycle, you start with a concept and then you evaluate from there. A lot of the methods that have been developed over the past 15 years haven't really gone into that industry. On the other hand, we are seeing a lot of changing paradigms, such as the shrinking of satellites, the emergence of CubeSats, the lowering of launch costs due to competitive satellite launch vehicle service providers. So we've had a lot of good changing paradigms for space exploration. But on the other hand, and that's also leading to federated satellites, where satellites are working together, kind of like a satellite society. Individual elements might be able to help each other out. So that's one of the next goals of research in different areas, is how do we get satellites who aren't even working on the same mission to help each other. On the other hand, there have been a lot of cost overruns in planetary science missions, such as with the Mars Science Laboratory. Other missions are exceeding their budgets, and that's leading to some problems because the science goals for these missions are becoming increasingly complex, and they're leaving a lot of the scientific stakeholders out in the dust. Not as many scientists are getting the scientific data they want, except for these very specialized areas. So one of the things that really struck me with this was, I was reading a paper and it saw that the combined exploration can help answer a lot of questions. This quote in particular, the combined exploration of Phobos and Deimos would lead to a far greater understanding of not just those two particular targets, but also Mars, Earth, and the formation of the solar system. So really one of the questions we have is, what scientific opportunity are we missing out on as a result of not being able to even explore the concepts with distributed satellites using their emerging capabilities? So this particular research area builds on a lot of what has been happening recently with distributed satellites and systems engineering. A lot of the methodologies, such as static and dynamic multi-attribute trace-based exploration, have gone into some of these previous studies of fractionated systems. However, those studies failed to include some of the methodologies like epoch era analysis. They also didn't look at the emerging capabilities. My research area also brings in some of the space science facts that we're going to be exploring. Fundamentally new objectives. How do we use federated satellites? How do we measure the science value delivery? So that's where this thesis research area is. It combines many elements into this area, which is one reason why it's so broad. So that's a basic overview of some of the knowledge capture and synthesis. Let's move on to the emergent capabilities definitions. It's really important to define these in such a way that we can understand them and how we would use them in these methods. So what I did for finding these emergent capabilities and defining them was I took previous research on the potential benefits of distributed satellites and also examined other scientific instruments that used multiple assets to accomplish their primary objectives. What I found, there was essentially three categories of emergent capabilities. The first category, fundamentally unique capabilities. These are things that you cannot do with a single satellite, no matter how expensive, optimized, or specialized it is. It can only be done by distributed satellites. The second category are the analytically unique emergent capabilities. These are the capabilities that allow you to gather data quickly and efficiently compared to a monolithic system, whereas in these missions, the monolithic system may only meet the bare minimum requirements. It's still possible, but it's very expensive, possibly infeasible. But with distributed systems, you can get a lot more data quickly. The third category is operationally unique capabilities. These allow you to explore risky environments and perform operational techniques that wouldn't make sense with the monolithic satellite. You might destroy your system and then you'd be able to get nothing with it, but with distributed satellites, you might be able to do that. It's not bad. So within this first category, I identified three emergent capabilities. The first one is shared sampling, and that's when different assets take responsibility at different times for taking measurements of the targets. We see that with telescopes around the world. If we want to take a 24-hour observation of a star, we have different telescopes around the world looking at different times. We also do that with pretty much every satellite constellation where we can get service at different areas. The second one in this category is simultaneous sampling. That's when you have multiple assets looking at the same target, but from different locations and different angles. We see that with seismology networks when we're trying to do seismometry, look for volcanoes and earthquakes. We also see it with 3D modeling and video capture, when you have multiple cameras taking a picture of the same object. The third category is self-sampling. Capability is self-sampling. That's when two satellites will look at each other or look at signals generated by each other to infer information about the target they're looking after. The Grail satellites measure changes in radio frequency to determine the gravimetrics of the moon. You might think aperture synthesis interferometry is also sort of self-sampling, but it's actually a combination of simultaneous and self-sampling. These radio telescopes are all looking at the same target, but then they're all looking at each other to develop the wider aperture overall. So that's the first category. The second category is analytically unique. The first capability within there is census sampling. It's when you have multiple azimuths making a lot of measurements of a lot of different targets to build up a database of information quickly. For instance, you wouldn't send one person around the entire country every 10 years for a census because it probably would take more than 100 years to get that done. Other types of things like all-sky surveys require a lot of telescopes. The second one is called stacked sampling. Now this is a little bit unique. It's when the combination of those data sets that you can get by exploring in different environments helps you answer more scientific questions than you had planned for from the beginning. For instance, anytime we've had a decades-long spanning science campaign to a planet, different information from different satellites has combined in such a way that we've been able to infer about a third opportunity, or we've gotten more value because they validated each other in some ways. The final category, operationally unique variables, or capabilities. The first one is called stage sampling. Imagine you're sighting a rifle, you can take several shots to gradually bring in your scopes to the right target. With this, imagine you have the ability to use information from your first deployed assets to determine where you want to send the next wave of assets. This information allows you to capture on scientific opportunity that you would not have realized with a single satellite, especially if that single satellite doesn't have the ability to travel to new locations. So we do this a lot with oil exploration. We drill a lot of holes in a lot of different places before we send the big rigs to actually pump that oil. The final capability within this category is sacrifice sampling. That's when assets are deployed to an area where you know there's a lot of risk, you know there might be certain failure, but the data that you can get before those assets fail will still help you answer those science questions. So if you've seen the movie Twister, you saw the little balls that had the little wings on them so we could see the fluid dynamics of the tornado. We've also done it with the Galileo probe. There was a probe that detached from the main Galileo satellite and went into Jupiter's atmosphere. That probe, which we sacrificed, gave us more information on outer gas giants than pretty much any other single satellite ever has. And that was because we sacrificed it. So, to answer the first question, research question number one, what are the emergent capabilities? Here they are. So, the next question is, how do we objectively rank science missions that leverage these capabilities? And that's where we're going to go with our method development. So, within the research approach, we've covered emergent capabilities, moving on to the methods, method development. So the method that I chose to analyze these space science mission case studies is called the responsive systems comparison method. It is a combination of two previously researched methods. It's called multi-attribute trade space exploration, and that's where we can take a look at a number of designs all on the same graph, basically. We're looking at the satisfaction on a scale from 0 to 1, where 0 represents minimum satisfaction, the least acceptable design, and 1 represents a design where you can't perceive it being any better. We can compare our satisfaction rating with the cost, and we can compare among many different designs. So that's MATE, and the second aspect of that is called epoch-era analysis. And that's where we can look at these designs as they evolve over their system life cycle, how they evolve in time, how our expectations may change over time, and how the operating context in which they change changes over time. So the responsive system comparison is a prescriptive framework for pre-phase A studies to characterize these missions and build up a lot of information so that we can eventually make the right design decision. We're not actually going to build millions of different designs, we're going to choose one that fits our needs the most. So the way I have kind of tailored this method, I put it into a 4-phase approach. The original one, other publications have used different frameworks. I just put it in this 4-phase approach to make it a little more approachable to scientists. The first phase is value modeling, and that's where we make a mathematical model of a mental preferences of these stakeholders, these scientific stakeholders, using an appropriate value-centric design methodology. The second one is the performance modeling, and most engineers are very familiar with this. You're building performance models to output attributes of the system. You're also looking at cost. Some people take cost modeling as a separate activity altogether. I just kind of wrap that into performance modeling. The third is trade space exploration, and that's where you explore your data sets and find what are called Pareto efficient designs. the ones that give you the most value for how much money you spend on them. And the final phase of epoch era analysis is where we explore those designs in time and see how the context can change and see how they can change in that operating environment. For today, I'm only going to be focusing a little bit on some of the changes I've made to this method to make it better for planetary science missions in the value modeling phase and the epoch era analysis phase. I can go into a little more detail during questions if there are other questions about what I've done specifically. So like I said, in the value modeling phase, you're looking to use a value-centric design methodology to build this value model. Of some of the possible ones that you could use, I found that multi-attribute utility theory appears to be the most appropriate for planetary science missions. For one, we are not looking at cash flow here. This is not a business venture. We're not measuring our satisfaction in dollars. Now, these first 7 properties of typical space science missions have been identified in previous literature. I also identified these last 2 to show that there still are some weaknesses here. These first 2 weaknesses are addressed with epoch era analysis and the responsive system comparison. But these last 2 weaknesses need to be addressed by other modifications that I've made to this method. So this first one, looking at how value is delivered synergistically, is actually built into multi-attribute utility already, but it just needs to come out in a little more explicitly. So this is one of the typical way to use multi-attribute utility theory is you have an aggregation of attributes that describe your satisfaction of the system, which you can plug into this equation here. For more complex systems, it's appropriate to have a hierarchy of attributes. So you can combine attributes within sub-attributes, and these can be combined within sub-sub-attributes. But one of the problems with this is how do we make this applicable to space science missions? So one of the things I did was I created a standard hierarchy. In space science missions, we get value by answering, we satisfy our top level goals. So at the top we have the science goals we want to achieve with the science mission and other primary mission attributes that might be especially relevant. Within each science goal, there might be a number of instruments that could possibly satisfy our needs, as well as other attributes that describe how well that particular goal is satisfied. And for each instrument, there are a number of attributes that describe that instrument. So when we're doing this, one of the things is we have these k-weights as well as the utility functions that come from the performance models. How can we interpret these k-weights in such a way that we can get synergy from it? So when the sum of those k-weights is less than 1, what we have is, so in this axis we have the single attribute utility for one attribute from 0 to 1. 0 is low satisfaction, 1 is high satisfaction. Another attribute here, and if the sum of those k-weights is less than 1, what we see is that as we move in one direction, satisfying only one attribute, we don't get a lot of satisfaction overall. However, once we start moving to satisfy more than one attribute, we quickly build more satisfaction overall. So for at this corner, we only have a multi-attribute utility of 0.15 when the max possible is 1 up here. So here's a way we can show and interview our stakeholders explicitly. How do you perceive the synergy between these attributes? On the other hand, if there is something called redundancy or substitution effects, I can have 2 instruments. If I have both of them, it doesn't really matter. We can do that with when the k-weights are greater than 1. If we go up any one of these attributes, we're going to get a lot of satisfaction, and it's going to cost a lot more, possibly, just to get a little bit more satisfaction by going on the other attribute as well. So this is where redundancy or substitution effects come in. When we do this explicitly, it really helps because it's not always elicited in that fashion in some of the previous literature. And so that's one thing I made sure I did when I interviewed my scientific stakeholders so that they understood what I was trying to do. The other thing is, how is value delivered over time in space science missions? Well, it's delivered in time in a couple of ways. You could have value delivered continuously, such as with the satellite constellation. It's operating every day, it's giving you value. You could have value delivered discretely, such as if you have mission events that happen on a schedule, you suddenly get buildups in value, and then you have to wait some time to get more value again. But in some space science missions, you might have value delivered pseudo-continuously, where you have value being created the entire time, but it's only being delivered at discrete intervals, such as when you're able to communicate with those satellites. So how can we not only take this, how value is delivered, but also how does that happen when stakeholders' perceptions of value might be changing over time? And one of the things I did with epoch era analysis was I made an assumption that this is not the generalized case of epoch era analysis where the expectations and the context can change very rapidly. With space science missions, your expectations are usually only going to be going up. So I was able to create another ranking metric based off utility, cumulative value, which is actually the integral of that multi-attribute utility over time. It's not applicable in the generalized case, but under certain assumptions, it is applicable for space science missions. So as a consequence of that, not only do we have a ranking designed for being able to capture the opportunity of space science missions, but it also gives us the opportunity, it gives us a metric to characterize the otherwise indirect, the otherwise unarticulated value that comes from some of these system lifecycle properties. So if I had one set of expectations where I had 1 satellite, 2 satellite, 3 satellite, something changed my expectations, suddenly 3 satellites is no longer good enough. But if I had 2 extra satellites, I could achieve that higher satisfaction. That allows me to objectively rank these in Monte Carlo analysis stochastically. So that also gives us another metric that I'm calling value at opportunity. If the expected value of your mission, let's say, is here, epic error analysis might be able to show that no, there's actually a possibility of getting more value of that. It's very similar to value at risk, which is where if you make a financial investment and there's some probability that you'll make less than your initial investment, this is the probability that you'll make more than you originally expected with a space science mission. So, in summary, the multi-attribute utility theory as a value-centric design methodology has some of those weaknesses, but because of the modifications that I proposed and used in these case studies, we were able to overcome some of those weaknesses. When there are multiple stakeholders, it does get a lot trickier, but there is current research within CIRI that is trying to address some of that to try to help that weakness as well. That is outside the scope of this research. So that is the method. Now we're going to go ahead and move on to the space science mission case studies. So for my research, I looked at 4 different case studies. Now these 4 case studies all had different operational destinations, all had different science goals, all went to different destinations, looked at a very different number of targets, different complexity with instruments, different architectural elements, even pretty different maximum number of assets that I was going to look at. The 2 things that are really important for this research in terms of how broad the scope is of the 7 emerging capabilities that I defined earlier, all 7 of them are being tested in these case studies. And all the different ways that value can be delivered, as I just explained, are being tested, including one that has a mix of both discrete and continuous value. Unfortunately, today I only have time to talk about 2 of these case studies. The first one is called HOBOCOP. It's the heliocentric orbiting baseline optimized cosmos observation paradigm. And this is a mission to study several aspects of the sun. The primary mission is we want to map the magnetic field, the solar wind, and a phenomenon called the heliospheric current sheet. This can be done with relatively simple instruments that we can put on small satellites. We don't require gigantic instruments to go really close to the sun. We can do this with small satellites, and we can do it better with many small satellites. So to give you guys a little bit of a science background, you may know that the sun goes through an 11-year sunspot cycle. That's actually a consequence of a 22-year rotation of the solar magnetic axis. So over a period of 22 years, this makes a full revolution. And one of the things we want to look at, scientists are very interested in observing the poles of the sun at opposite sides of the sun, both poles at the same time, during this period of time. That's during the 11-year cycle from solar minimum to solar maximum. Another thing we want to look at is the solar wind. What we see here is the sun is in the center, and this is Earth. You're looking at a coronal mass ejection that occurred in August 2012. Earth got hit pretty hard here, but didn't take the brunt of it. But the only measurements we were able to take were with some of our satellites. This is stereo A and stereo B. We don't have a whole lot of measurements of the solar wind from different radial distances from the sun. So there's a high desire to get some of that as well. Finally, the heliospheric current sheet. This is a model that I made in MATLAB showing the Parker spiral. As the magnetic axis of the sun rotates, and the sun rotates once a month, the area where the magnetic lines reconnect along the magnetic equator carries a current, and it goes out over time, and that's kind of what it looks like. We also want to get in situ measurements of that to better understand that. So, without imagining any specific design, here are our 3 science goals, and here are the ways we can sample it. How can we satisfy these scientific goals? How can we conduct in situ measurements and remote observations in a rapidly changing field? The way we can do that is by leveraging the emergent capability of simultaneous sampling. So, I'll go ahead and describe some of the architectural elements of this mission. This mission is actually based off the concept of hobo sensors. They're like little weather stations. You can program them throw them out in the wilderness, come back a year later, download all your data, and then leave them again. You don't need to be in contact with them all the time. What they can do is they can communicate with Earth or a relay satellite relatively infrequently. So we have the primary spacecraft bus, which contains all the instruments, a solar shield to protect it from heat, and then an expendable electric propulsion module that carries all the fuel it needs to get to its destinations. Now, when I originally came up with this concept, here's what I was thinking was about a 2U CubeSat that carried magnetometers and maybe a fast particle analyzer, carried its solar shield that was thermally separated. But once I started talking to some of the scientific stakeholders, I realized, we need another instrument here. So this is our in situ payload, but there's also an observation payload that carries an instrument that's called a vector field magnetograph. This is an instrument that allows you to measure magnetic fields using pictures, different wavelengths, and the changing of those wavelengths. So it's part spectrograph, part telescope, but it does give you a full picture of the magnetic field of the surface of the sun. So these two different payloads have two different concepts of operations. This first payload has a concept of operation that looks like this. First, we start out in a near-Earth orbit and begin an electric thrust maneuver. That would take us to the operational orbit where it would jettison its propulsion module and then enter its operational orbit. Its operational orbit would take it close to the sun. At its closest approach, those solar panels would fold in. And then once it gets near the top of its operational orbit, it would communicate with either the Earth or a communicating orbital platform, otherwise known as a COP, relay satellite. So here is an animation I made in SDK showing how one particular design of this satellite constellation might work. We see all the satellites starting near Earth, and as they burn, you see the red represents when they're burning, and the yellow satellites are when they're in their operational orbits. What you're seeing is they're actually working together, making these measurements, so that they can take multiple passes longitudinally around the sun simultaneously. Not just longitudinally, but also latitudinally, because they're at different inclinations. This gives us a wide sampling range of the solar wind and the heliospheric current sheet, and that's what we want. That's what the scientists desire in order to build better models of the solar wind and this current sheet. For the observation payload, it can't go as close to the sun because it's carrying a telescope. It can't have a heat shield. So what it does is it uses a much shorter burn to enter a half-year period orbit. Once it's in this orbit, it makes its closest approach. It doesn't jettison its propulsion module, but what it does is once it comes back to where near Earth is, it either conducts another burn or uses a burn and an Earth flyby to raise its inclination to get into a solar polar orbit, which is very difficult to do otherwise. It's only been done by leveraging Jupiter gravity assist. But because of electric propulsion, we are able to get higher and higher inclinations, and so that's one of the design variables I worked with. Here's another animation I made in SDK showing 4 satellites and how they would go about getting into these polar orbits. When they're yellow, that's when they're just cruising, and when they're red, that's when they're either burning or using an Earth flyby. And so over the course of a couple years, what we see is we end up with 2 different satellites on opposite sides of the sun in polar orbits. Here's 4 in particular, and that's how we can go about getting what those scientists want. So looking at the value model, phase 1 of the responsive systems comparison method, we have our science targets, we know our instruments, we know our types of operations. We also realized from the interviews with stakeholders that there is some synergy in the way that these instrument attributes can operate. And so that's what we see here with the vector field magnetograph. Another thing that was very important was understanding the measurement lifetime. We want to make these measurements from solar minimum to solar maximum. So lifetime is actually very critical in terms of what we're doing here. We want to make sure that we're operating over a long enough period of time. There are a few other things I want to point out here. For measuring the photosphere magnetic field, the scientists said that 1 viewpoint was good enough, but that a lot more satisfaction, was achieved with 4 viewpoints. 4 is, that was the maximum perceivable satisfaction they could have for the observation payload. But for the in situ payload, the sampling resolution is actually much higher than that. Many more assets are needed to get the sampling resolution of the solar wind and the current sheet that we want. Another thing that was interesting was how quickly satisfaction dropped as we got further and further away from the sun. That's because in this area here, that's where the solar wind is actually, it's called subalphenic, sort of subsonic in the speed sense. The solar wind starts slow and is eventually pushed faster so that it is at supersonic speeds by the time it gets to Earth. And we want to know, more about that area, what happens in that particular area, and that's why satisfaction drops off the further away our closest distance to the sun is. The other thing is we want to make sure we're sampling out of plane from the sun, up and down along the axis, along the ecliptic plane. So here are some of the considerations that our scientific stakeholders told me about, and I was able to elicit a value model of. So in addition to the primary context, I also looked at a number of other contexts, including especially how technology can affect this mission. This mission takes these small satellites and uses an incredible amount of delta V to get to where they need to go. Each one of these satellites has more delta V than any other mission that has ever been launched. So I want to make sure that this is actually feasible. So what I did was I used some of the SMAD-based assumptions and some of the best-case assumptions to see which ones might be feasible and which ones might be infeasible. I also looked at a couple different value models. One, especially looking at the sensitivity of the attribute weights within goal number 1, the one to look at the solar photosphere, and how that might change things. We also looked at different communications and whether or not there was a federated network of satellites to tap into during the course of the mission. So these are sort of the alternate contexts that could be operating in. That comes up later in the epic error analysis. Within the performance model, phase 2 of RSC, I looked at over 10,000 different designs, different combinations of these different design variables. Combine that with 24 different epics, I looked at over 250 design epic evaluations. Now I want to point out one of the more important design variables is the payload package. So these were the 5 different payload packages I looked at. These first 3 represent the in situ payload. They could be carrying a magnetometer or a fast particle analyzer or both. For the observation payload, it could be carrying the vector field magnetograph, or it could be carrying all 3 instruments. So one of the interesting things here was that I noticed that better satisfaction could be achieved if we used a combination of them. The sampling range, radial sampling range, is actually better if we can use combinations of these assets. Another thing I saw was an emergent property on the shape of the constellation, depending on which assets we were using. I just kind of ramped up the number of satellites really high, ran some orbital simulations, and saw that these shapes are the shapes that they're sweeping out. Even though each one of these dots is going on their own elliptical orbit in time, they're taking out these sampling sweeps, and that might actually be detrimental to the scientists' satisfaction criteria. Turns out it wasn't, but because of this, we looked at heterogeneous sets, took possibly 1 or 2 of the more efficient designs, and ended up looking at 1.3 million design epics just of combinations. So if you have 10,000 designs and you're trying to combine more than 2, it becomes computationally expensive, so I never considered more than 2 at a time just because I wasn't able to. But what we see here is we do see some good results because of those heterogeneous assets. So what we see here is the trade spaces for goal number 1, looking at the photosphere, goal number 2, looking at the solar wind, goal number 3, looking at the heliosphere current sheet. What we have on this axis is our satisfaction from 0 to 1, and on the x-axis is the cost, and this is the total mission multi-attribute utility, the total satisfaction we get here. So these blue dots are payload 4, that's the one that are just carrying the vector field magnetograph. As we expect, those payloads are the most efficient because they can accomplish this goal the best and the most efficiently for the lowest cost. However, it doesn't do a very good job at achieving these other ones because they don't even carry the right payloads for it. For the other 2 goals, the ones that carry the magnetometer, that's what we see in red, and just the fast particle analyzer, that's what we see in green, those are some of the more efficient designs at the low end because, again, they're only carrying the payloads that answer that particular question. However, once we consider the synergy between the satellites that are at the far end, far away from the sun, and the ones that are close to the sun that give us a wider sampling range, that's when we start to see the bump in the value that we get out of these systems. And those are these yellow dots that have the mixed payloads. And that's what we see overall, is we see a big jump in the synergy that we have. And that's why all of these designs are the ones that are going to give us the most value. So what we normally look for in a trade space is the special points where there's what's called the knee in the curve. That usually gives us the best design before you have to spend a lot more money to get more value out of it. There's a better example of the knees in the Pareto curves in a little while. So just so you're aware, this is the point where we would like to be. We have high satisfaction with very low cost on this side. Now we're going to show the epic analysis. So this graph right here is about to move to right here. So this is the primary mission context where the one I just showed you, but then there's also alternate contexts that the mission might be operating in. This one shows the pessimistic technology era, and what you see is there's a shift because it's going to cost more to get the same performance out of those designs because of how much heavier they need to be and how much more power they need to bring. There's also dots that are not shown here because they are infeasible, because they can't survive that close to the sun as a result of different material properties of the heat shield. For our alternative model, we see actually a little bump here looking at how the stakeholder might view the mission differently, a bump here as a result of how they view that goal in particular. So we can see some of the sensitivities here, and it's much more obvious when we consider both of them. Finally, in epic error analysis, one of the things we looked at was the failure rates of satellites. Even if satellites fail at a normal rate, the value that you get out of a mission might not follow a normal distribution. For instance, we see a couple different families of different ways of how satellites fail. Within this first group, we see those are what happens when the in-situ payloads fail. But if one of your observation payloads fail, that results in a much bigger drop, and there's a possibility that you might have zero value out of this mission because you don't meet your minimum expectations. That's something we can do with epic error analysis. The other thing I took a look at was what is the added value of being able to connect to a relay satellite network. So if you're only able to contact Earth once a year, one particular design showed a 30% chance of falling beneath the minimum expectations, even though it was designed so that it would meet expectations. But if you're able to contact it more times per year, the probability and the risk goes down further the more you're able to contact these satellites. That gives us information on whether or not we should even bother dealing with relay satellites or whether we should build those. So it's not answering the question, should we use relay satellites? It gives us a framework to decide whether or not we should. It's not my job to answer that question. That's someone else's decision, but I have delivered a framework to be able to answer that question. So for this case study, in summary, we leveraged simultaneous sampling to achieve our primary goals. Unintentionally, we also leveraged stack sampling, and that's where different goals can combine together to give you more scientific value. That was unintentional from the start. So that ties back to research question number 1. Research question number 2 relating to the methods. Because of the methods that I chose to employ, we saw the complementarity in our attributes, which led to synergy within our multi-attributes. And because of the epic error analysis approach, we saw how there was an impact of technology, how those secondary value models might change the design that we ultimately choose. And we also saw how we could reduce risk via federated satellite systems. So that's the end of the first case study. The next case study is GANGMER. It's groups of atmospheric nanosatellites and ground penetrators for Mars in situ research. You might know it as Odin's Spear, also known as GANGMER. That's what this mission is named after because of the ground penetrator aspect of this. The primary science goals of this mission, we're trying to achieve the top priority goals for the future of Mars in order to send humans there. There are a number of goals related to both the atmosphere and the ground. For one, no rover has ever dug more than a few centimeters beneath the surface on Mars, and we don't know whether or not there are any biohazards down there. We also need better atmospheric models for entry, descent, and landing when we send large spacecraft there. So, a little bit of science background. The atmospheric goals are trying to get us to be able to land on Mars better. We want to take a look at the atmosphere in high detail over a period of 5 years, and we need to have at minimum diurnal coverage. We want to look at every part of the planet at least twice per day. We also want to take a look at dust storms and their frequency, as well as aerosols and that sort of thing. So that's the atmospheric background. For the subsurface side, we know there's a lot of water based on gamma ray spectroscopy data from Mars Odyssey. But we don't know whether or not there could be anything beneath the permafrost more than a meter deep. We want to know what the bulk water content is, the regolith, and we also want to look for biohazards and other signs of life, one of which is molecular chirality. Different molecules might be able to be formed in different configurations. If you see a wide abundance of one particular hand over the other, that means that could be a sign that life once existed. That could be subsurface. Another interesting part with some of these Mars science missions is the site selection process. Every time we launch a probe to land on Mars, there's a conference, there's a bunch of people that come together, and we whittle down the number of science targets. What eventually happens is a less risky approach takes place, and the landing site is chosen based more on the engineering constraints than how interesting the scientific location is. So as a result, there's a lot of areas that are scientifically interesting that have not been explored. How can we explore those areas? How can we take that risk? If we only have one super expensive satellite, there's no way we'd ever send that there. Or sorry, one super expensive rover, we'd never send it there. So without putting a form to the science goals, here are the goals. Top two are to search for subsurface biohazards and observe the global temperature field. There's also a number of other goals that are high priority for Mars exploration. How do we go about solving these goals, or satisfying these goals? How do we sample from both ground and orbit? We can leverage stack sampling. How can we visit all these risky targets and explore all these locations? We can use a combination of staged and sacrifice sampling. So this is the mission concept. There are a couple different architectural elements at play here. The first is a small satellite. That would be the orbital payload. The second is a ground penetrator, which would go into the dirt, slam right in, dig down, take a sample. Or you could have a combination of those two types of assets such that you could use the penetrator to deliver a satellite or two to their respective orbits before then going down into the surface. So concept of operations for a single penetrator looks like this: performs a descent burn, jettisons its propulsion module, impacts the surface. The drag shroud will stay at the top, and that contains the antenna communication system. A sample drills a sample, and the instruments analyze that sample, and that data is then relayed to the orbiting mothership that's in an eccentric orbit. And it's in an eccentric orbit because that helps you deploy a constellation of satellites without having to use a lot of propulsion. So one of the things about Mars is very oblate. It's actually flatter than Earth is. As a result, through orbit propagation, if we go over time, what we see is that causes the precession rates of different orbits to be very different. So without burning any fuel over the course of a month or two, we're able to deploy a full Walker constellation with no extra fuel for the most expensive burns you can do, which are inclination changes. Additionally, these are limb sounding instruments. We have both limb sounding and ground pointing instruments. So we're getting a pretty good range of coverage because they're spinning around. Their spin rate is dependent on signal to noise ratio and that sort of thing. But that coverage element also got involved in this modeling process. So here's what we really have. We have upward pointing remote sensing, in situ subsurface, limb sounding atmospheric measurements, and ground pointing nadir measurements. So with just these two different types of assets, we can do quite a few things. So I'm not going to go into too many details on the value model like I did for the previous case study, but the important thing here is how do expectations change with these penetrators? What would it take for us to want to say, hey, I want to take another measurement at this location? How valuable is the next penetrator that I have, whether or not I have any? For instance, in our primary value model, given a certain number of penetrators and sites we want to visit, we achieve full satisfaction. But if during the course of our mission we make a minor discovery or even a major discovery, that would shift our expectations about how we view the value of that mission. How much can we react to the information we have here? So for some probability of a minor discovery, you might say, okay, the next penetrator that we have, whichever one we can launch, could add the rest of the value to our satisfaction. Or if it's a major discovery, we definitely want to measure it again. That next penetrator is pretty critical to total satisfaction. And so what that is, that's an endogenous shift in our expectations. If we didn't carry enough penetrators, we might not have discovered it in the first place. We would have been ignorant to it. So that's why it's a little harder to model in the traditional epoch era analysis sense, because the context change depends on your design that you choose. So we'll come back to that in the epoch era analysis part. But for now, we'll go into the performance modeling phase. There were a number of different variables we chose here, especially looking at the different packages that each of these assets could take. So for the satellite, it could have a camera, a radiometer, or both. And there were a number of different spectrometer and weather packages that we could have on our ground penetrators. Overall, over 10 million designs were evaluated in this mission based off of this design vector. So as a result of so many designs being evaluated, I had to make some simplifications on the instruments themselves. For instance, instead of being able to look at design variables with the full spectrum as they had for the small satellite, for the penetrator, I just looked at different packages that were available. So for instance, if there was a spectrometer package that had value 2, it included an accelerometer, a drill, a mass spectrometer, and an X-ray spectrometer. Same thing for the different weather packages. There's different groups. If you step up, you add an instrument there. But for the small satellite, I did an actual trait space for those variables. Each one of these is a sub-trait space, and the more sub-trait spaces you have, the bigger your trait space gets overall, so you don't want to get too high there. So the instruments on the ground penetrator were actually modeled on other recent studies for lunar penetrators and Europa penetrators, whereas the small satellite instruments were based off of the Mars Climate Sounder for the radiometer and commercially available CubeSat cameras for the ground pointing instrument. So phase 3 is trade space exploration. There were a couple different interesting things I found here. One is there's a lot of tension between our science goals and the design variables we have. For instance, the radiometer's aperture diameter, as you get bigger to bigger resolution. But as the wavelength, your maximum wavelength increases, that means your pixel size has to increase, which decreases your resolution. In order to achieve all of the science goals, you want to have the largest wavelength, but the highest priority goals are satisfied with the lower wavelengths. So for priority number 2, we have this low wavelength here, but for the least high priority goals for our weather instruments, we need the highest band center. So the number of bands we have is basically relevant to the size or maximum wavelength. What we see is there's kind of a sweet spot with 7 bands if we're on the cheap end within that radiometer to take those measurements. So there's other design variable tensions that we can explore through trade space exploration, but this is the one that was the most relevant here because that drastically affected the cost of the mission, because as your aperture goes up, your mass goes up almost as a square. So here is part of the trade space. It's a little heavy here, so let me explain. We have our satisfaction from 0 to 1, and we have our estimated cost. All of these dots represent designs that have a 2-to-1 ratio of small satellites to penetrators. These other lines are the Pareto fronts for other configurations. So this blue line is designs that only have small satellites. This purple line is for designs that only use penetrators. And this gold line here are for when you have a 1-to-1 ratio of those elements. So first thing we see here is, compared to single asset designs, we see a lot of synergy in this area. We can spend more money developing these assets, or sorry, for the same cost, we can get a lot more satisfaction compared to these only using penetrators or only small satellites. But you also see that the relationship between 1-to-1 and 2-to-1 is pretty similar as we get up toward those Pareto efficient designs. So that's trade space exploration. Now the final phase, epoch era analysis. Because of that epoch shift that could occur as a result of the change in expectations due to information that comes during the course of the mission, what we see is that if we have some probability of survival or failure and differing number of penetrators, depending on our expectations, for one, the more penetrators we have, we practically eliminate the risk of our mission becoming unsatisfactory or not being able to launch even a single penetrator. But what we also see on the other side is that there's a much higher probability that we will achieve a greater value than what we expect, and that's the normalized value 1. That's what we designed for. As we go up with the number of penetrators, there's a much higher chance we'll get more value out of that. So not only does more penetrators eliminate that risk, but as the number of penetrators increases, we see the value add opportunity increases. By the way, Danny, I'm sorry I haven't been shouting this out. We're on slide 76. So the expected cumulative value is much greater than what it's designed for as a result of the way we can characterize these missions using the responsive system comparison method. So for different expected probabilities of failure, of probability of making a follow-up measurement, of making a big discovery, we see that the average over the expected value goes up over time, but we also see that the value at opportunity drastically increases at the point once we go from 5 to 6 penetrators. It goes up because that's kind of the point where the value of 1 penetrator it becomes lower than the added value that we would get as a result of being able to capitalize on the value of follow-up measurement. And that's very important because that's something that we have to elicit from the scientists. At what point do you have more penetrators than ordinarily you get from a single? When you have more penetrators than you would expect to get value out of a single one of. I think that made sense. But there reaches a point when the cost of those penetrators compared to the value of those penetrators drops enough that that's when you get that big spike in the value and opportunity. So when we compare the trade space again, it's harder to see if we're looking at the entire trade space. So instead of doing a side-by-side comparison, here's a difference graph. Here we see the change in the cumulative value as a result of the number of penetrators. So what we see is for these penetrators here, they were never valuable to begin with. They didn't meet the minimum expectations. But as we raise the number of penetrators, you're seeing, not only are we seeing a decrease in value because of the risk, we're also seeing a decrease in value up to a certain point just because we're getting more out of it. We have higher expectations. And then once we hit a certain point, then we start rising again. So the more penetrators we have, the higher expected, or the higher cumulative value we can expect from those missions. And this is not only important just for showing this, but this metric can be applied to a lot of those other system lifecycle properties as well. So the conclusion here is, even though the original trade space said 1-to-1 is pretty good, it's pretty close to 2-to-1 ratio, a 1-to-1 ratio of satellites to penetrators is much better because we're able to capitalize on this extra opportunity. Yes. So, tying this case study back to the original research questions, we intentionally leveraged stage sampling and sacrifice sampling to get more value out of the penetrators. We also leveraged stack sampling to get value to take measurements from both the atmosphere and the ground. Unintentionally, this mission can be seen as leveraging 6 emergent capabilities. To some degree, if you have simultaneous samples from ground station, you're taking a look at global weather. You're also leveraging shared sampling because you have a constellation of satellites. You're doing census sampling if you're sampling all these different sites that you want to go to. So this is a case study that really uses a lot of these techniques that we would need to use, but I mostly focus on these 2 in the development of the mission. So research question number 2, going to the methods. If we hadn't done the value modeling process, we might not have seen the complementarity at the instrument level. And because of the trade space exploration, we saw the synergy between the ground assets and the orbital assets. Most importantly, from this case study, we saw that the previously unarticulated value of being able to take advantage of opportunities that arise over the course of the mission, we are able to quantify that now thanks to valued opportunity and the cumulative value metric. So that wraps it up for the approach. We're done with the space science case studies missions. Now let's go ahead and talk about some of what we can conclude from this. So combining phase 2 and phase 3 of this research, one of the goals was, okay, what techniques do we use for which particular emergent capabilities? And that's what I've done here. For certain techniques, for certain capabilities, it's actually kind of self-evident that you need more satellites to conduct those missions. For instance, most satellite constellations, if you know your coverage, it needs to be a certain level, then you pretty much know you're going to need the extra satellites. But for stage and sacrifice sampling, it's much less obvious. And the metrics and the different things that I've done to improve the responsive system comparison method for application to space science missions have really helped on those later capabilities that we define. Now, within the emergent capabilities linked to the space science missions, none of these missions would have been accomplished to this minimum satisfaction criteria without leveraging these capabilities. Each one not only leveraged one or more, but for instance, the first case study, Exoplanet Sat, a single satellite's unable to do the coverage we need of stars. The second one, we would be unable to achieve the in situ resolution we want. For an asteroid exploration study, there's no way we could feasibly get the data we wanted in time to make a positive net present value for that mission. And for Gangmere, there's no way we would have gotten the coverage or been able to visit as many sites as we wanted to meet those satisfaction criteria. Now, within linking the case studies to the method development, we learned a lot of things as a result of the method that we would not have learned if we hadn't gone through all 4 phases of the responsive system comparison method. So not only did we find an optimal constellation, and I have not used that word throughout this presentation because optimality is not important for trade space exploration, but we did find a way to make an optimal constellation for that mission. We were able to quantify the benefits of allocating different assets in HoboCop. We were able to identify how different stakeholders might change their strategies depending on their value models in Gangmere. And with Gangmere, we quantified the true value of the operational flexibility. How can we get more value out of a mission as a result of being able to react to situations as they occur? So one of the unforeseen consequences of this was the range of science goals that we explored here. So you might be familiar with Donald Rumsfeld's classifications of known knowns, known unknowns, and unknown unknowns. There's actually a much better classification from McManus and Hastings that shows statistically characterized unknowns, known unknowns and unknown knowns. What I saw was that still not quite good enough. There's not quite enough resolution there. What I saw was a spectrum of knowledge that can be applied for these science goals, and how well we understand a science goal before trying to push it from one end to this. So every time we want to answer something in science, we're always pushing in that direction. What I didn't realize until the end was, these science goals kind of span this range. There were a lot of different science goals here. And why that's important is that different science goals and different levels of knowledge require different techniques and approaches. One of the things I talked about was value-centric design methodologies and how multi-attribute utility is appropriate for a lot of cases. It's actually not fully appropriate. Sometimes you might be able to find a mathematically explicit model that represents the stakeholders' expectations. So for instance, what I discovered, and this is sort of my opinion, is that as we go from the completely unknown into the statistically characterized phenomenon, there's a higher probability that you're able to find an explicit function to answer this, and that's what I saw with ExoplanetSat. But once we go from statistically characterized into being able to describe individual phenomena and predict them, that probability drops again. And so we were able to use multi-attribute utility here and here, use a statistical function here and a combination of statistics and multi-attribute utility for a here. So specifically within my thesis, I contributed the definitions of emergent capabilities of distributed satellites. I made specific improvements to the responsive system comparison method and some of the interview techniques that we use to interview the scientists. We mapped the emergent capabilities to specific techniques within responsive system comparison. And each one of these 4 case studies can be used not only within the SIRI lab as a data set for future systems engineering exploration, but also missions on themselves in case anyone wants to take these to the proposal phase. In addition to all that, I did some work on astrophysical constellations for ExoplanetSat and developed a model to get year-round coverage of a target using a constellation. And then I also contributed some to federated satellite networks and understanding how to kind of gauge the price points and where they would be valuable. Before we conclude, I just want to point out that each one of these 4 case studies could be a master's thesis in and of themselves. About 90% of what I talked about was only 10% of the overall effort. This is really where most of the effort went into the engineering models. Even though we talked a lot about the value proposition and the science, most of the effort was underlying, and I didn't have time to talk about that today. So that leads us to the final thought. Yes, I believe I have proved to you that there is scientific opportunity that we can capture by using distributed satellites. And we can capture that by leveraging the new techniques that I've tried to help develop here within the responsive system comparison as it already existed. So, thank you.
So we'll take this opportunity to ask questions. I don't know if we want to have a closed session. There is an opportunity to have that with the candidate afterwards, but if not, we can stay open and have the faculty ask questions as well. Okay. So who would like to ask a question?
I'll start with a couple. First of all, this was a very, very complex topic, very long thesis, and I think did a great job of condensing it into a presentation here, so congratulations for that. Could you go to slide 28? Yeah. So, talk a little bit, you show the goals and attributes on the same line. Could you talk a little bit about how those are distinguished when you actually get into the mathematical model?
So you say here?
Well,
or
in any of those, you've got goals and attributes.
So,
yeah.
So these, for primary mission attribute, that might be something that applies to all your goals, or some other facet of the design that affects all of the goals, or is from the top level is perceived as important on the same level. So you might
illustrate that with an example. Maybe it's a little bit vague.
So I would say you could say mission lifetime was your attribute here, depending on, like you could put mission lifetime here or here, depending on whether it's different for your different goals. So, so for like the weather goals on Mars, I ended up putting the mission lifetime here, but for the Hobocop mission, I put the mission lifetime here because it affected all of them equally. I can probably think of a few other examples, but it depends on the mission itself. Why the goal would also have an attribute here, but in general, it's how important is that particular attribute compared to the entire mission versus is that attribute only important to a goal?
Slide 50. And the deal there, I may have missed that in looking for the thesis the first time, but you're talking about X-band or Ka band, but this is with CubeSat type satellites.
Small satellites, yes.
Getting K-band antennas and powers that normally are necessary for that sort of communication. How are you able to accomplish that with a small CubeSat?
I actually talked to Alessandra Babusha about that. I originally wanted to have a much bigger trade space on the antennas because I felt like that was an important part of this, but I had to kind of de-scope some of that exploration. And so what I did was I asked her about what's sort of the top of the line X-band antenna that we could use, and she gave me some specifications on that. And then I said, okay, what if it was that same exact antenna just with Ka band? So the power, depending on whether you're talking about the power emitted or the transmitter power, I assume those were the same, and that's why they're completely different contexts, because they wouldn't really exist in the same model. But I did get that information from a source.
And the last, this would be slide 76. It was just a question. It turned out to be what looks like a bimodal distribution, which I wonder if you, yeah, there you go on the right. Is there an explanation of why you have a bimodal distribution there?
Yes. So remember with those epoch shifts, how much our expectations shift. Mm-hmm. The idea was a major discovery would it actually increases our expectations, but on a scale from 0 to 1, that shifts our previous expectations down. So that's represented by this number 1 here. Essentially, it doesn't work out quite the same mathematically, but you might be able to think of it as if you double your expectations, this is where you could be able to say this is where we're going, even with a low probability of having something that shifts your expectations so high. Because in this particular example, you have 9 penetrators, there's 8 different opportunities to take information that you got from a previous penetrator to go on that. So not only, that's where the bimodal part comes in, but then you also see this extra value here. That's a result of that smaller shift as a result of the smaller shift in expectations.
I'll leave it there for a while.
Sure. So Ben, you commented in your motivation that there are a lot of new methods out there in system engineering that are not being used. Kind of framing it as if that's something that you're going to try and tackle. Can you comment a little bit about how you foresee impact of your work and affecting how practices on that regard?
Part of that involves how well this work is disseminated into the engineering community. I guess what I would like to see is a change in the concept proposal phase, or at least the concept design phase, especially the pre-phase A's of not just NASA's exploration program, but also any other agency that's doing space science can apply these techniques. NASA's Systems Engineering Handbook has 2 paragraphs on pre-phase A. And I know that other concurrent engineering design studios have their practices, most of which don't put enough emphasis on the stakeholders and really eliciting the value that comes for those. But also, from the scientist's point of view, how can we think about what we get out of a mission, what does give us value, rather than coming to the concept stage with preconceived notions and biases for those notions they have. So I would like to see a lot of changes in the way we do that, but it's going to take, time for this to kind of go out and get more practice. The more successful examples there are of this type of thing in use, the higher likelihood that it will be more widely adopted. Did that answer your question?
Partly.
Okay.
So in one of your earlier slides, I forget which number, you said something about having objective means for ranking alternatives as an outcome of your second research question. Can Can you expound a little bit about what you mean by objective and how contingent that is to the assumptions you made in your
Sure. So when I say objective, trying to eliminate the preconceived notions or people's pet projects or pet ideas of what they want to have for their design. When you focus on value-driven design, you focus on what you're trying to deliver first, before you ever put a form to what you're trying to accomplish. So by kind of removing those and applying a lot of different concepts to the same value model, you can explore which concepts give you the most value for the resources you have, so that the choice isn't polluted by personal effects or personal bias, if you can extract the value model in a non-biased way as well. And so when we say that's objective to the value model, it's also objective to the designs themselves, because we can look at those designs and we can rank them based on their performance and how well those designs meet the value model. But then within the scope of not just monolithic versus distributed, but other distributed satellites versus distributed satellites, the indirect benefits can also be quantified. And so when we add those in, that gives us a little better idea of how we could benefit from not just the indirect value from the system lifecycle properties, but also how well they leverage the immersion capabilities if that's a mission you're trying to do.
Can you go to slide 31?
Sure.
Can you clarify for me whether you are imposing an assumption of constant multi-attribute utility definition in order to accomplish integration?
Sorry, can you rephrase that?
Sure. So in order to integrate that function, it needs to have constant meaning. So what is the implications of that assumption? Is that a necessary condition for your work?
Yes, because as if the context changes, one of the assumptions I make is that we're going to be looking back at these missions near the end of the mission. Rather than, we're not looking at these into the future as they can go, like you might do with a military system where the context can change back and forth. This is valid only within a single epoch. But if we consider the entire system life cycle, we sort of evaluate it using the epoch we reach at the end.
So it's retrospective?
It's retroactive, retrospective way to rank the designs using this metric.
Okay, slide 53. Okay, so you talked about objectivity and preconceived notions and things like that, but was there any room in your methodology to come back to the stakeholders to say you have to separate? You actually would do better with two separate missions entirely. Because we always wondered from the start, there were other preconceived reasons, right, why we started out, when we started out with getting near and wanting to combine the atmosphere and the penetrator. And the question is, from this plot, when I looked at it, and just realized this while I was doing it this time, it looked like I'd be better off in terms of cost to have two separate missions. Actually, I didn't mean this was the wrong one. I wanted to look at the one for Mars, actually.
Okay.
I'm not sure which one what the equivalent is for Mars.
Oh, sorry.
Actually, let's go back to 53. I
Okay.
was wondering about for Mars, but I think the 53 slide shows the issue. So let's see. So let's say you have the three goals, right? You have the total.
Mm-hmm.
In each of the three goals, it looks like in some cases, in one maybe, you actually get close to one. Like, what if I just wanted them? If you went back and said, look, you can have 100 million, you can have 100 million, or you can all get 200 million. Like, did your model allow for us to have that first scenario?
It could. There would be a few other complexities in terms of calculating costs, but I assume that they were completely separate development cycles.
Right, because look, if you take like the bottom left and the top right plots, and I say if I look at the mean, the curve, let's say for 100 million each, current sheet and solar wind can get something, I don't know if photospheres can get something in this mixed one, but I feel like they did better because on the bottom right, I didn't see a case where we had, although that's not each individual, that's your overall, value. I didn't get close to one. So maybe does the model in any way, able to get rid of that preconceived concept that they all have to work together?
I mean, you could treat them as separate missions, but when you combine the value models, that's also a separate. Combining value models is actually a little difficult because not everyone ranks value the same way, and that's another reason why we're getting nowhere near one here. That doesn't mean it doesn't mean 0.6 is really disappointing. It just means this is a ranking. These ones are the ones that give us the best. But that's not what you asked. What you asked was, can we separate them? We can separate the missions, and that's kind of what I did. I treated them as separate cost development cycles. If they have different engine sizes, they're going to be entirely, I just treated them as two separate satellite programs and didn't apply the same cost discount functions to them. But if you're just separating the value model, so if you had two different stakeholders, then it's possible. But trying to combine those two different stakeholders' value models is difficult, and if that's what you're asking, that's still an area of active research.
Okay. My second related question is one that you heard before, but it's how do you validate the model?
So which model, performance or value?
Well, the whole thing, the whole four-phase model. Like maybe just pick two of them and tell me how you would validate it.
So for a value model, Nico Ricci actually went to some pretty specific details on how you can validate that. One of the easiest ways is to basically, you have all these designs, and you can pick, a design here and a design here that have two different utility rankings, and you can say, which one do you like better? If the stakeholder tells you, oh, I like, the one that's higher, but I like this one better than this one, then okay, that's a pretty accurate value model, depending on how far away they are. Obviously, this design and this design probably going to be. You're probably going to know that this one's going to be better. But once you start choosing designs on the same line, if the stakeholder doesn't really have a strong opinion about which one is better, if they can't decide, oh, both of those look really good to me, I really can't decide. I'm indifferent to these two different options. That's when you know you've got a pretty good value model. Again, Nico went into a lot more detail on different ways and techniques to validate those models. For the performance model, that's also, there's a lot of people who validate performance models. Most of what I did was with SDK and MATLAB. I compared, most of my validation was through comparison. Like for my orbit module in Hobocop, I had the STK model, wasn't working fast enough for me, so I built my own MATLAB model, and I compared the results for a few different models, so there were some comparisons there.
That's it.
Done.
Is there a compatibility between Richard's time-weighted utility loss and your cumulative value ranking metrics?
I'm not too familiar with that particular metric of his. What time-weighted value loss?
Time-weighted utility loss.
Is that similar to sort of like a net present value discount?
Not really.
Okay. I did take into account some time-weighted utility loss in the 8-year mission, because if you have discrete value delivery over time, but it takes several years compared to a mission that you could have today, yes, I did take that into account. For the two missions I presented, the utility only increased in time because it was a constant observation. But I did have another case study where we looked at, okay, I can have something, the exact same data set now or 3 years from now, which one's better? Obviously the one that's now. So I did take a look into, the scientists' ideas of their perception of that utility.
One other question. There's been a lot of work previously and a lot of attention now to the expert versus novice in trade space exploration. How much expertise do you think is needed in terms of the stakeholder set that you would involve in such a study versus being able to involve people who have less experience?
One of the things that I saw was for doing the stakeholder interviews, I still had to, teach them quite a bit just to get them up to the level where I could properly interview them. So that was kind of difficult. For for showing an audience what's going on, I guess it's not that particularly difficult. It's like, okay, so here's the mission, and you can pretty much tell them why this design is better than this design or something like that. But you do bring up an interesting point. Are you asking like when would you get them involved, or it's?
Well, maybe even what's the mix of people that you would need? Could you, like, it's always a challenge in these types of studies to get the best people, the most experienced people, and so oftentimes studies can suffer from the fact that they're maybe staffed with people that don't have as much expertise, but some people will argue that this type of approach helps novices to do things in a way that only experts have been able to kind of do in their head.
Gotcha, yes. I do agree with that. I think, so each of these missions is, I was sort of the lead on all of them, but they're really better designed within a concurrent engineering design studio. I think because, you get a team together, you can knock these out in a week. I think there needs to be at least one expert level person to be able to do that. I don't think there needs to be too many more. I was imagining sort of what would Team X do. Team X is a concurrent engineering design studio at the Jet Propulsion Laboratory, and they would, they have their kind of science representative. And I think if you had one more person in that team that was sort of the trade space expert, they would work very closely with that science representative and the stakeholders. That way, most of the team would at least know the basics. Okay, we're trying to get these attributes. What are the attributes? What do we need to model to? I don't think you need that many people on a team as experts. So it really depends on what you say by novice level, I guess. If it's, if everyone in this room is now novice trade space exploration because of this talk, then yeah, that's, but if novice is they've actually gone through and played with something like IVT, then, I think it would benefit everyone just to have, maybe a few hours of practice and lecture on here's why we're doing what we're doing, here's how to do it. That would help for everyone, but really I think you only need one big expert. Sydney. Oh, Danny, do you have any questions?
Sure, thanks. So I guess my first question is methodologically you have a number of contributions, essentially in the trade space exploration field, right? So I was wondering if you have any ideas of what's next, what are the next steps, what is the next problem or theme that needs to be solved methodologically speaking related to your thesis?
I want to say there's still some methods involved with the interviews with scientists. I did struggle with that. There might be a better way to formalize some of the psychological aspects of this. So there's definitely a lot of work on a lot of different areas. I think there also needs to be more case studies that use the cumulative value as I proposed, just to sort of do a little more validation of what I've done, or maybe get a little more data just to see, and a little more actual validation of the techniques I've made. There may be other metametrics that I have not applied. I know that Michael Schaffner's thesis dealt with a lot of those. I didn't really apply those as much. So are you talking specifically within the broader scope of the methods, or the methods as they apply to planetary science missions?
I guess both. It could be generally in trade space exploration, things like the multiple stakeholder issue, if you think that's an important issue,
yeah.
Or more as applied to TSS.
Right. Well, I know Richards is focusing a lot on multi-stakeholder negotiations, which is kind of, I want to say, is the last big weakness with multi-attribute utility theory. And that is difficult just because everyone perceives, different levels of 0 and 1 for minimum and maximum satisfaction. I'm trying to think if there's anything else. I know the epic error analysis. What I would like to see in there, one of the things I did was I sort of just assigned probabilities for when these events might happen. If there was a better way to look through previous scientific missions and talk to the scientific stakeholders to see, how much they would have valued a change in their mission, how much they would have perceived the value of being able to react to a mission. I would like to see some more data there, so we can make better predictions with the epic shifts there.
Mm-hmm.
So that's a few suggestions, I guess.
Okay, I do have a follow-up question, and this is really a tough question, a hard question. I don't really think I have an answer, but I would like to hear your thoughts if you have any. One of the things that one of the challenges, one of the most important challenges I think we have with this kind of work is the killer question that, how do you ensure that the low fidelity models that you're using for trace space exploration work are consistent with the higher fidelity models that are going to be used later on. So I was wondering if you have any ideas, if you guys have given any thought to that.
I actually have given some thought to that, and one of the, I guess the simplest way to deal with that is to screw up, to make a model that's too high fidelity, realize you don't need it because the model takes too long and it just doesn't matter, and then take a step back and use your lower fidelity trade space model that runs a lot faster. One of the struggles I had was with the entry, descent, and landing module with the Mars mission. I was working with a group of Italians. We made this 3D model, including the Coriolis effect and an atmospheric model, and then we looked back at the stakeholder definitions and realized they don't really care about landing site accuracy that much. We're just trying to get it within 100 kilometers, not within 10 meters. So we bumped back down to the lower fidelity model. In other applications, what I recommend doing is comparing the lower fidelity to the higher fidelity model. If you know you're going to have to come up with the higher fidelity model later anyway, you could at least start that during the trade space exploration part to make sure that a few of your designs are actually running correctly, and then run your lower fidelity model later. What it really comes down to is how well that model answers the question of what is the attribute level. So that's my kind of thought there.
Okay, great. So my last question is sort of a big picture question, and it's related to sort of barriers of implementation for these kind of missions. So I was wondering if you had some thoughts on what you think are the strongest or the most important barriers that are currently hindering the application of these kind of mission architectures for both earth science and space science, really. So do you think it's a technology problem that we don't have, I don't know, formation flight, for instance, technology? Or is it more of a political problem, or a little bit of both?
I think it's definitely political. I don't think there are many technological problems that we can't overcome, but without the politics behind it, that's one reason why we can't overcome this. You mentioned formation flying specifically. None of my missions actually require formation flying, which also helps simplify a lot of the value or the performance modeling. But the big thing is how do we make a change within government organizations to say, hey, we're going to use these methods. We're going to use these methods from now on because they work. That's what it's going to take, really, I think. How does value-driven design get implemented into these agencies?
Okay, well, thanks.
Yeah, you're welcome.
Thanks. So one question I have is at the beginning of the design, there's a lot of uncertainty and a lot of the analysis has been done. I mean, you use low fidelity models that they're good for what they're good for, which is the design phase, but may not agree with later things. Plus, you have these interviews with all these people, and you get sort of feedback, but sometimes it's a function of what questions you ask. So it boils down to a question of just how dependent are the assumptions you're making in the analysis and generating these plots, and sort of where does the uncertainty and everything that went into this show up in the answer? Because if you showed a point where you sort of had some graphs and said that if something happens, the graph goes down, and you get a different plot. And just now you're talking about the probabilities of these events happening, but do those have first order effects on the answers? I mean, it's really a sensitivity question, right? This is an answer, but what's the sensitivity of this answer to every assumption you put into the problem? And how do you convey that to someone that's saying, this is actually a pretty robust design setup, right?
So actually, this method is sort of a way to do validation and sensitivity analysis up front. That's the beauty of this is, you could have a performance model take a month just to calculate all your attributes. But with your weightings, you can quickly redefine those value attributes and see, how those sensitivities would change. So when you talk about talking to these stakeholders and how they might change their mind, you can quickly see, which designs might change a lot, which designs might change a little. There are a number of other metrics that I didn't talk about, such as fuzzy Pareto number, a normalized Pareto trace, that can show you, okay, these designs are relatively insensitive to the changes that could occur, or how our models might be off on the value model side. For the performance model side, we're still dealing with phase A, pre-phase A exploration. Even cost models can be as high as 50% off. So there are a lot of uncertainties. We can account for a lot of them and see how they change the result of that. And I didn't really show a whole lot of that here, but that is something that's built in from the beginning.
So you propagate the uncertainties through the entire analysis and generate these sort of, I don't know, the Pareto front graphs with the uncertainty sort of embedded in there as well?
I wouldn't say embedded. It's normally, for the trade space exploration part, it's usually just not that important. Even though in any other type of analysis, uncertainty usually is very important, but that's how we can explore that is with these other metrics. For trade space exploration alone, not considering the uncertainty can be detrimental, but that's where epic error analysis helps with that. So I don't have error bars on all these just because that would clutter it up too much.
No, understood, but the question typically is, are the differences between the designs significant on the scale of the uncertainty in the problem that you currently understand?
Well, considering all designs are kind of made with the same model, if there is a change, so if performance model, they would shift a lot in the same direction as a result of the changes you would make. So they're all subject to similar levels of uncertainties.
I'm not sure I agree with that statement.
Okay.
All right. Who else has got questions? Move more everybody out. Okay. All right. Let's thank the speaker, and then I think the next phase is the committee meets, and we invite everyone else to leave. Thanks.